All right, so we're going to talk about electric heat. Electric heat is electric, woogie, 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 to quote the electric slide. This is starting bad, really bad. We already talked a little bit about electric heat when we did the heat pump heating diagnostic and troubleshooting and servicing section, but we're just going to kind of keep rotating through as we go. So one thing you are going to need is you're going to either need the calculator on your phone or a scratch pad with paper. I think we'll do the calculator on your phone for most of you here, because we're going to do just a little bit of math, just a tiny, tiny bit. Bert attempted to do some of this in his class. And I think it's helpful when you're going to give a class for something that you actually know what you're talking about before you give the class. That's usually something that I advocate for. Not that I'm picking on Bert. We're going to do just a little bit of math. We're not going to focus on math because math is not the main thing with this. We're mostly going to focus on just the relationships, what happens when different things change with electric heat. So the first thing is I always start with a story. I've told this story like 1,000 times, so if you've heard it before. You know what story I'm going to tell, Sam?
I could tell it.
Which one is it going to be? Because there's two.
I prefer the bank one.
Okay, the bank?
Yeah.
Okay, you want to tell that one?
No, it's better for me.
Okay, it's better for me. Okay. Well, I wasn't going to tell the bank one, but I'll tell both stories. Actually, let's just start with both stories. Start with don't bury the lead, is what they always say. So the bank story is I was probably 19. I was doing maintenances for a bunch of SunTrust banks. They used to be called Sun Bank back in the day. And I was actually doing the maintenance on the one in Claremont. And they have a big rooftop unit that does most of the bank and a couple splits. But I was going through and I was testing the heat strips because I was told that that's what you're supposed to do. So I was running them in heat, and I was doing it just by jumpering out to white. So jumpering red to W, and heat strips would come on, and I would check the amperage and whatever. Well, I was doing that, and as I was doing it, because I had to set an extension ladder up against the parapet wall on this bank, the bank manager came up, poked his head up and said, "What the heck are you doing? There's smoke billowing everywhere. The bank's on fire." And so I'm like, okay, shoot. And I come down, and sure enough, there's they've already got the doors open. There's smoke billowing, and the fire department's already pulling up. Well, as it so happens, my parents bank there, and so my dad shows up while this is all going on. "Hey, what's going on? Let's talk about it for half an hour." And so I finally, we got it all cleared out. Of course, I wasn't very popular in the bank. And then got done with all my maintenances, left, and then I think I was either the on-call tech, or the on-call tech called me and was like, "What did you do? The bank is like 95 degrees, something like that." Maybe it wasn't even on call, maybe it was just later in the afternoon, because banks aren't open that late, so this story isn't really working too well. But anyway, so it was really hot in the bank, and so I show up, and yeah, it's like super, super hot. I go up, and this package unit was a heat pump, and it was running in heat mode. So like, what gives? Well, as it turns out, when they had originally wired up the smoke alarms were supposed to break red in order to shut the unit off when the smoke alarms went off. Well, they didn't. They broke orange. And so when you break orange, you have no 24-volt call on your reversing valve, and it just locked the thing in heat mode. And so I didn't test out the way I was supposed to. So a couple mistakes there. One is, whenever you're going to check electric heat, especially if you don't know when the last time it's been tested, you need to talk to the occupants. If you think it's been a really long time, like in a commercial application where maybe the heat strips have never run, it's a good idea to just pull them out and clean them with some compressed air or nitrogen or something like that, rather than burning them off. So that's the lesson there. That was a great story, wasn't it? I feel like I really told it dynamically there.
I had a little bit more since last time too. So.
You didn't know about the no, that was true. It's true. I didn't make it up.
Oh.
I just haven't told that part before.
Good.
So that's just a lesson in being thorough. I was thorough, but I wasn't communicative about my thoroughness, and then I wasn't thorough in the end in testing out. The other story is about, I forgot what the other story is. Hold on. What was the other story that I always tell about electric heat? Oh, there is actually another story that I'll tell a little bit later about wire sizing. That's another key one that we'll get to. So the other story I want to tell was I was working on a package unit in Leesburg, actually. Very close to where you live nowadays, Sam. I know that adds to the story, just having that personal connection to the story. Yeah, okay. So I was working on a package unit, and at that time, the company I was working for, they would give us heat restring kits. So they had a failed heat strip. It was shorted out or open or whatever. It was actually burned, and they gave us this kit, a 5 kilowatt heat restring kit. So it had the entire thing. It was in a little plastic bag, and you were supposed to take it and restring this whole thing, put it back on the insulators and all that. That's what we had on our trucks. It's the first time I'd ever done it. So as you can imagine, I kind of bungled it. As I was making the terminations or whatever, it kind of kinked and like broke, and it was in bad shape. So I thought, well, this customer, it's just heat strips. So if I take a little bit of heat strip off, just a little bit, the part that's broken, that's not going to hurt anything. It just won't heat quite as well, right? Does that stand to reason? Stands to reason that if you take a little bit of heat strip off, it just won't heat quite as well. Does everybody agree with that? It'll still heat, it just won't heat quite as well. Just took a little strip off, right? Okay. Here's the problem with that. I knew Ohm's law and Watt's law, but I didn't pay very close attention to it. And I don't care that you know how to do the math or don't know how to do the math, but Ohm's law is E equals I times R, okay? So that means that voltage equals amps times resistance. Well, in this case, the voltage is fairly fixed going into a unit, right? So that part is the part of the equation that's fairly fixed. So we'll say that our voltage is 240 volts. So 240 volts equals amps times ohms, all right? So if 240 is fixed and I change ohms, which is what I'm doing when I cut a piece off of that heat strip, and I change them down, does my amps go down or up? If I decrease my resistance, the amps go up. This is a very simple concept, so you don't even need to know the math. You decrease resistance, do you get more flow or less flow? You get more flow, right? You decrease the resistance in a pipe, do you get more or less water flow? You get more flow, you decrease the resistance. You increase the resistance, you get less flow. Easy. And so what did I do when I cut a piece of heat strip off? Did I decrease the resistance or did I increase the resistance? I decreased the resistance. I took some of the coil off. If you take some of the coil off, there's less resistance to electricity. Do I get more current or less current? I get more current. So what happened was I took a piece off, and when I lit it up, when I fired it up, it was drawing high amps, and the thing was glowing red and didn't work, right? So, and I don't know, maybe it was glowing red because I was testing it without proper airflow over it. Who knows? At that time, I was a dummy and didn't know anything, so it's hard to know what exactly I was doing. But the point is that with heat strips, if you reduce the resistance, you're going to get more current. And so that's what happens sometimes when heat strips touch a piece of metal. You create a short circuit path, and they will burn out because they're drawing too much current. Make sense? So it's important when you install heat strips, one of the most important things is that you don't short them out. You don't short them out to the casing around it. You don't short them out to each other. Pretty obvious. You will run into cases where things will lay across here just in the installation process. Sometimes they're, something like a piece of ductboard or a piece of cardboard or something which will catch, the cardboard will catch on fire, the ductboard won't do much other than block airflow. But sometimes it could be metallic, and that can lead to heat strip failure. Make sense? So make sure that you don't do that. Benefits of electric heat. That's what we've got up on the screen here. One nice thing about electric heat is the math is really easy with electric heat. 1 watt equals 3.41 BTUs all the time. So here's a question. This heat strip here, is it more or less efficient than an electric space heater? So if I took this to heat the house, or I heat a house with a bunch of electric space heaters, which is more efficient? This, right? You agree? You agree? This is more efficient. Well, no, it doesn't matter. In terms of, now you could, once you add in the little motors for everyone, maybe it's a little more efficient. But in terms of the heating function, with electric heat strips, no matter if it's a little tiny heat strip on a space heater, no matter if it's an oven coil, no matter if it's the element on your oven or on your stove, they're all going to equal 1 watt in equals 3.41 BTUs out. Just that simple. And so if you've ever heard of COP, coefficient of performance, COP is a measurement where you compare the efficiency of a refrigeration device or some other device that moves heat around to electric heat, and it's always more efficient. So a typical COP for a pool heater, for example, would be like a COP of 3, something like that, which means that it's 3 times more efficient under normal operating conditions than if you were just running electric heat to heat the pool. Make sense? Because in the case of electric heat, we're taking electrical energy and we're converting it directly to heat energy. Electrical energy directly to heat energy. In the case of the refrigeration circuit, what are we doing? What are we doing with heat? Ronnie, refrigeration circuit, what are we doing with heat?
Getting rid of it?
We're getting rid of it, but we're moving it from one place to another place. So we're not taking one form of energy and converting it directly to another form of energy. We're taking energy from one place and moving it to another place. That's the definition of refrigeration, is to move heat from a place that it is unwanted to a location to where it is unobjectionable. You remember that one? Unobjectionable. That's what it is. We're taking heat and moving it from a place that we don't want it to a place we don't care, basically, right? But in electric heat, we're taking electricity, turning it straight to heat. So it's not efficient. But one nice thing about it is we can count on it. We know what's going to be produced. It doesn't matter. It doesn't matter if it's 0 degrees outside. It doesn't matter if it's 90 degrees outside. It doesn't matter. It doesn't matter. It doesn't matter. Electric heat, 1 watt in, 3.41 BTUs out. It's reliable. Super simple, right? Electricity in, heat out. No moving parts. Very simple. And it's easy to work on. So that's the good news. What's the bad news? Well, one of the biggest things, and this is the main thing I want you to take away from this, when we work in a market, which we do, where we have a lot of electric heat strips, we need to make sure that we burn them off. We need to test them at least once a year. And we need to let the customer know that there's going to be some odors, maybe even some smoke in extreme cases, if it hasn't run in a really long time, when we first test them. So that is an indication to the customer that we've done our maintenance. If we do a fall maintenance and they first run their heat come December, right at Christmas time, right when we don't want to be working and we want to be with our families, and there's a bunch of stinky smell, what are they going to do? They're going to call us because we were supposed to do the maintenance and we didn't do it properly. So at least burning off the heat strips is critical. It's very easy to do. So quick poll here. What's the very easiest way to burn off heat strips? Most simple way.
Either remove it from the unit and turn it on and let it burn off outside.
Yeah, you wouldn't want to do that, because if you remove it from the unit and you apply voltage to it, it doesn't have airflow over it, so you will destroy the heat strips. Heat strips are not designed to run with no blower. In fact, they will. That's why they have these thermal limits and stuff. So if you pulled it out of the unit and you did power it up, they would heat up and they'd go off. They'd heat up and they'd go off. So you could do that, be fairly dangerous, not the suggested way.
I mean, you should already be in the air handler, so W to R.
Yeah, W to R, that's it. You take your white circuit, white low voltage circuit, jumper it to your red low voltage circuit, and heat strips come on, you measure the current on them, you let them burn off for a minute or so, and now you're good to go. You make sure they go back off once you take the jumper out. That's the easiest way. Now, why isn't that a perfect test?
Because you don't know if the thermostat would actually call them on.
Yeah, you don't know if the thermostat's actually calling it on. You don't know if it's actually going to work, but at least you know that they're not going to smell up the place, and at least you know that there's nothing wrong with the strips themselves. So now you've tested the heat strips on the high voltage side, but you haven't tested the controls. Is that okay? In some markets, yes. In some markets, no. Right? In our market, heat strips aren't that critical anyway. And in fact, we would probably benefit in many cases by not even having them in terms of people's power bills. So in general, that's going to be a perfectly fine way of testing your heat strips. What's a better way to test them that's not quite the most extreme, but is also a good way? Yeah, at least use single.
Through the thermostat?
From the thermostat, but doing it through the thermostat service controls, a service menu where you actually go in and you drive on electric heat. So you go into running your second stage heat and then you test it. So you're not jumpering it, you're telling the thermostat to do it. You're still not running it under normal conditions, because normal conditions would be to go to the thermostat, set the temperature way up, and then wait for the thermostat to turn the heat strips on. Problem with that is some thermostats have built in an algorithm that either uses outdoor temperature, like the modern fancy ones. It won't even allow them to come on if the outdoor temperature is high enough, and we're going to talk about that. Or they have a time function, so it has to run a certain amount of time before it's going to let it come on. So you could just be sitting there a long time, depending on the settings. So probably not your best way. Going into the installer setup or to your installer service setup and just driving on that mode is probably going to be a better way.
The Ecobee is like the easiest for that, the test equipment.
Exactly.
Yeah.
Yeah, test equipment, also Carrier Infinity, same thing. If you go up and you're doing a maintenance or a service on a Carrier Infinity system, just go through into the installer setup and set it into the mode you want it to run in. And then that way you can actually test all the different modes very easily. Because you actually get a readout too of a lot of your key readings right from the control. That's kind of nice.
Well, a lot of that, even the less fancy thermostats, there's an emergency heat option.
You got emergency heat option.
Well, yeah, but it depends on if emergency heat is actually connected in the way that it's supposed to be. With a lot of modern thermostats, that's kind of, you put in emergency heat, it calls for W2, but on older thermostats, and we're going to talk about this, a lot of times that E isn't actually even hooked up. So it depends on how they're wired. Heat strips are extremely inefficient. So we do not want heat strips to run unless we need them to run, and that's some of the strategies that we use have to do with that. So they can cause high bills when they run too much. High current can cause electrical damage. This is another thing. So heat strips are one of the highest current drawing devices in the entire home. There's almost nothing in your home that's going to draw a continuous, and this is just 5 kilowatt, a continuous 20 amps at 240 volts. That's, nothing else in your house draws that much current, which means that nothing else in your house is it as important that the electrical connections and the wire sizing and everything is correct. I'm going to pause here and let that sink in. Not your compressor, not your dryer, not anything else in your house. That electric heat strip is going to be one of the highest, if not the highest. I said your dryer is also a pretty high one. But, so that's where electrical connections are really key. And one of the big mistakes I see people make, one of the things I want to protect you from, when you're going in and you're a genius because you've gotten good with electricity, and you know how to diagnose things, and you know how to rig things together, when you're dealing with electric heat, and this is also true of gas furnaces too, they would even be higher on the list. Don't go in and start rigging things up without paying attention to the wire sizing you're using and making sure that those electric heat strips go on when they're supposed to, go off when they're supposed to, and aren't run through a relay that can't handle that current. That was a complicated sentence that I just used there. The point is, don't run it through some sort of control that can't handle the current. And that's easy to do because it's a lot of current. Make sense? So wire sizing to a system that has heat strips in it is going to be one of the most important elements. Even if you're, say, all right, I have a burned up wire inside this unit. Well, I'm just going to grab a number 14 off my truck and wire it back up. In fact, one of the guys who I worked with at my previous employer before I worked here, he actually got let go because he rewired heat strips with just a roll of number 14 off of his truck, not paying attention to the fact that it obviously isn't going to handle the current that it was drawing, and it ended up creating a little fire inside the unit, which was very problematic. Make sense? So just quick poll, 20 amps, what size wire does that need to be typically? Number 12 wire, right? Typically, that's the size wire that you would use. Now there's some exceptions to that rule, like we talked about in a class that we did recently on wire sizing. But generally speaking, that's what we were looking for. Another common issue is mistakes with blower interlock. So we want to, and we're going to talk about how to wire these, but blower interlock, back to kind of what Mario was talking about earlier, we do not want to run our electric heat strips if we do not have blower running. And so we have some method to make sure that if the heat strips are running, the blower also runs, and that's what we call blower interlock. Sometimes that's done on low voltage, sometimes that's done on high voltage, but it always has to be done in some way. Something that makes sure that those heat strips, or that the blower runs when the heat strips are on. Why? Why do we need the blower to run when the heat strips are on?
Potential fire hazard.
Potential fire hazard, right? They get very hot, very hot. And so if they keep cycling on and off, on and off, on and off, something gets in there, it could potentially cause a fire. And then stress on the electrical service. This is another one. So when we go from a gas furnace to a heat pump with heat strips, can we just count on the fact that we can just swap that? Just, hey, you got a gas furnace, we're just going to put a heat pump in with heat strips. No, we can't count on that. You got a lot of older homes that are running gas that may have a 100 amp service on the house. So you may be able to slam an electrical panel in there. Well, hey, I can put a new panel in, run some new wires, put a breaker in, good to go, right? But did you think about the breaker that runs the entire house and the wires that feed the entire house? How often do we think about that with what we do? Like never, right? Because that's not my job, right? Not my job to worry about that. That's the electrician's job. Well, if we're not calling an electrician out to look at it, or we're not thinking about it, then we could potentially overload the entire home service, which could be a potentially dangerous problem, especially in older homes that aren't wired very well to begin with. Maybe you have the old rag wiring or whatever, or aluminum wire, for example. You still have
a 100 amp house where you probably wouldn't put above a 5 kW in anyway, but you've seen it with like a 10 kW.
I've seen it, yeah. And again, we're not qualified to do electrical load calculations because it's not just as easy as just adding all the loads up. Like, it's not like that. There's like a whole formula. There's a whole sheet that you have to fill out in order to do that. The point just being that if you go to a house that has a 100 amp service on it, this is even 125, and you're pulling a furnace out, stop. Ask the question. Look at what else is in that home and see, is it going to be potentially a problem? Because let's say they already converted a gas dryer to an electric dryer. Okay, well, they're right there. You've already kind of screwed up, and now you're just going to keep adding to it, keep adding electrical appliances to it. So it's not always, in many cases, it's not a huge deal to upgrade a service. It's not like the end of the world. Maybe $4,000 or $5,000, something like that. But if that has to be done, it has to be done before we put our system in. And even inspectors aren't often going to blow the whistle and have you stop because they're not going to think about it. It's a change out. They don't think that, oh, you changed out a furnace for a heat pump with heat strips or a straight cool unit with heat strips. Make sense? Cool. All right, let's do some math. This is going to be fun. Bert's really good at this now. He's an expert at this math. Right? Right?
Yeah.
Am I right or am I right? Am I right or am I right? All right.
Oh, man.
All right, so let's do some basic math here. How many watts is a 5 kilowatt heater? All right, so we're going to say it's 5,000 watts, right?
Yeah, we are.
All right, now, this heat strip here, let's see what it says on it. It says that this is an 8.9 kilowatt heater. So this is what we'd call a 9 kW, right? If you look at the individual heat strips, these are 4.45 each, right? So if we're going to do the math on this, we would have to do it that way. But we're just going to do the math on the board here. So you have 5,000 watts. We're going to divide it by whatever the rated voltage is for the unit. So let's say that, well, let's look at this one over here. Look at what we got here. We've got, it's got a rating for 208, it's got a rating for 230. And actually it says right here, heater watts, 4,600. We would call that a 5 kilowatt heater, but it's actually only a 4,600 kilowatt heater at 230 volts. So it says that right there, 230, 4,600. So let's do it that way instead.
208, isn't it? That's 208, right?
It has both. So it's got 230.
He's just looking at the tag.
Yeah, I'm literally just looking at the tag. So it says right here, 4,600, 230, 3,750 at 208. What just happened there? Let's stop and address that quickly. So this is only 3,750 watts at 208. Why does the wattage decrease when the voltage decreases? What is voltage?
Current.
Amperage is current. What is voltage? Voltage is potential or electrical pressure. So we're putting more electrical pressure on the circuit, right? You put more pressure, do you get more current flow or less flow? More pressure, more flow. Less pressure, less flow. This is also resistive load, so there's less going on in it. It's a more simplistic circuit than a motor. So it's very steady, like we talked about. You put 1 watt equals 3.41 BTUs. All the time, all day, every day, right? So let's use the math here. If we go to 230, we've got, what did I say again? 4,600? It's right here on the data tag, 4,600. So that's what we're going to use. We're going to use the one that we've got here. 4,600 watts at 230 volts. Okay? So if the calculation is E equals I times R, we first have to get our current out of this. So how do we get our current out of this? Well, we have Watt's law too, which is a really simple one, which is watts equals volts times amps. So all we got to do is divide our watts by our volts, and it gives us our amps.
20.
And what's interesting about that is if you look on this data tag over here, it tells you exactly 20 amps. If it was 208, it'd be 18 amps. So if we do that math, that's how it would work. All right. So now, let's figure out how many BTUs this bad boy produces, this particular heater. This is really easy because we already have the watts, right? We did the math. This all adds up. 20 times 230 equals 4,600, right? So now, what are our BTUs?
So didn't that say 3.41?
3.41, yep. So we take 4,600 watts times 3.41 equals what?
68, 69?
So wait till we get a consensus.
15,686.
15,686. Right? So that's how many BTUs we're getting out of it. So we're getting somewhere between a ton and a ton and a half of heating capacity out of one 5 kilowatt heater, which ain't much, right? It's a lot to get that much, right? How much BTUs do we get out of 20 amps normally on a running system? You know, you may have a 3-ton system that's giving you, that total is drawing 20 amps. By the time you add the compressor, the fans, transformer, everything, right? So you can see you're not getting much in terms of BTUs based on what you're spending here. Make sense? So that's the math. Now let's go ahead and change one of the variables and see what we get. Okay, so right now we're matching up exactly with what the data tag says. And so that's handy, it's easy for us. But what happens if we change the voltage? What happens if we change the voltage from 230 to 240?
Not much. Your amp shell's going to go up a little bit.
Our amp draw is going to go up. Our wattage output is going to go up because we increase the pressure. Now the problem is we cannot do this math this way. You're going to be tempted to take this and multiply that times amps and get watts. But the problem is that the amps also change when I change that. We have to go back to Ohm's law, okay? And in order to do that, we have to figure out the resistance. You're going to notice here we don't have the resistance anywhere on this board. We didn't figure out the resistance yet. So let's go back. If E equals I times R, E is voltage, I is current or amperage, and R is resistance in ohms, okay? Volts, amps, ohms. So what do we know? We know in this case that our voltage is 230 divided by 20 equals what?
11.5.
11.5. So what we know now is that the thing that stays the same, or pretty much the same, it actually does change a little bit, but because things actually change in resistance as their temperature changes, but generally they're pretty stable. Now we know that the heat strips are 11.5, and that's the thing that doesn't change. That's the part that's not a variable, actually, right? That makes sense? The resistance of that heat strip doesn't really change, because we can change the voltage, which changes the amperage, which changes the wattage. All that stuff is a moving target, but the resistance isn't a moving target, right? So now we've got to delete amps, because amps change when we change volts. We've got to delete watts, because watts change. We've got to delete all of this. So what are we left with? We're left with whatever our input voltage is, which we measure, so we're going to say that goes up to 240. Right? E equals I times R. So we know E, 240, equals blank, question mark, times 11.5. So now we divide 240 by 11.5. What do we come up with?
20.86.
20.86. What was it before? 20. At 230 volts, it was 20. Now when we increase our voltage to 240, we now get 20.86, and now we can figure out the rest of it again. 20.86, multiply that times 240, what do we get? 20.86 times 240. Now we're doing Watt's law, amps times volts.
5,006.
5,006. So now we have a 5K heater. Before, did we have a 5K heater? At 230, it was 4,600. Now, at 240, it's over 5,000. So it's actually not an insignificant difference. Now, we take that, we multiply that times 3.41 equals what?
Oh, 17,070. It says decimal, but.
So now that is our BTU output. So you're never going to do this math. Okay, I'm not doing this for the sake of you doing the math. I'm doing this so that you can understand what you really have in a heat strip. What you really have is essentially a fixed resistor. Stays the same. I really had my hand on my hip there. That was really iffy.
So pretty.
It really was. It was kind of, yeah, it's nice. You have a fixed resistor. And now depending on the voltage that we apply, that changes the amperage. And once we have the amperage and voltage, that gives us our wattage, which then gives us our BTUs. And you can see that 10-volt difference not insignificantly impacted the amount of BTUs that we output. If we drop this down to 208, it's going to be a huge drop in the output. Make sense? Everybody get that? Okay. So that's something to know about these because they're not like a compressor in that way. They're fixed resistance, whereas a compressor or a motor, the resistances vary quite a bit depending on load. These are pretty fixed. All right, so what's proper wire size to feed an air handler? Well, the easiest way is just to look at what the data tag says, right? It's going to tell you what your MOCP is, or your MCA, minimum circuit ampacity. It's going to tell you what that is. So you base it on that. We're going to typically size our wiring based on our standard 60 degrees Celsius column, which is like, you know, your safe zone, and that's going to be, if you got 30 amps, number 10, 20 amps, number 20, so on and so forth. Now, if you have 10 kilowatt heat, that's where it gets tricky, because what do we normally run? What do most people run to a 10 kilowatt heater? Size wire. Number 6 is typical, but is number 6 60 amps? Number 6 in the 60 degree column is actually 55. So you have to use slightly better wire in order to be able to use number 6. You can't use number 6 Romex in order to do that. So, and again, all these charts are readily available. This isn't a wire sizing class. We've already done that class, but you know, ad nauseum, right?
All wire size.
All right, so we talked about this. It isn't always 5 kW. Just because you see a single heat strip that looks like this, don't count on the fact that this is a 5 kilowatt heat strip. It's an individual heat strip, but look at the actual strip to tell you what it is, or look at the data tag. And right here, it shows you 4.45 kilowatts at 240 volts on this one. This one's rated at 240. What was this one rated at on the data tag? 230, right? So it changes. It's an interesting thing because even when you look at, it's just a silly thing that happens. When you look at what it tells you the breaker size should be, what the MCA is it telling you what we actually have here in Florida? No, it's telling you 230. What do we actually have in Florida most commonly? What voltage do you typically see in houses? 245, right? So what's going to happen to your current on a heat strip that's running 245 when the data tag says 230? It's going to run higher current, which means what? Does that mean that is that data tag valid now in terms of what size wire it tells you to put on it? The answer is yes, it is, because it's what we got. But it's kind of a goofy thing that manufacturers do. Sometimes they're going to give you 230, sometimes they're going to give you 240, but even 240 isn't enough. That's why you're going to see amperages on your heat strips that are higher than 20 amps. If your voltage is higher, your current's going to be higher. Your wattage is going to be higher, your BTU output's going to be higher. All right, let's talk about some of our different terminal designations here. Letters are a little small on this slide, but so W. When we see W, W just means heat. Does it mean heat strips? No, just means heat. So generally speaking, W is going to be used on old school furnaces where you only had a single source of heat. And so it's just W. W, white, that's heat. Bring the furnace on, right? W1 means first stage of heat, which could mean in a heat pump is what? What is first stage of heat in a heat pump? Carlos?
Is what?
First stage of heat in a heat pump.
First stage, the reversing valve?
It's the compressor. Yeah, the compressor with the reversing valve de-energized typically. That's first stage of heat. W2 is electric heat in a typical single stage heat pump. But beyond that, you know, you could have a system that was a straight cool system that had 2 stages of electric heat, and W1 could be 1 stage, and W2 could be both heat strips running simultaneously. So it's not always the same thing. And then W3 would be the next stage. And so if you have 2 stages of electric heat on top of a single stage heat pump, then W3 would be your second stage electric heat, but you could also have a system that has 2 stages of compression, like a 2-stage compressor. W1 would be first stage compressor, W2 would be second stage compressor, W3 would be heat strips. That's why when 2-stage compressors first came out, we had to use 2-stage cool, 3-stage heat thermostats. That was a really big deal to find them that were that way. There weren't a lot of them made. The old Honeywell Chronotherm back in the day was one of the first kind of fancy thermostats, and you had to get the one that had the 3 stages of heat in it. Because, first stage is first stage compression, you get what I'm saying. So, and then emergency heat is usually just a way to manually drive on your backup form of heat. It really is not ideal for heat pump markets where you only have 5 kilowatt heat, because what it does is it locks out your heat pump mode and it only drives the electric heat, which usually isn't going to do much of anything. If it's 20 degrees outside, do you think this little 17,000 BTUs is going to do much to heat a house? No. It's going to do very little to heat a house. So, it's better than nothing, I guess. But generally speaking, we're not going to use emergency heat much. In a market where you have very large heat strips, or in a market where one of your stages of backup heat is actually a gas furnace, well, now that makes perfect sense. Because there are markets, they call it, hybrid heat or whatever, where you actually run the heat pump when the temperatures allow for it, and then you get to a certain point and you shut the heat pump off, you run the gas furnace. And in that case, if your heat pump's failed, you put it in emergency heat so it just runs the gas furnace. That makes perfect sense. Right? Make sense? Cool. This illustration shows kind of an early way that we used to wire up thermostats, where we would actually have to always jumper aux and E, or W2 and E together. We'd have to actually put a physical jumper in. There used to be a lot of physical jumpering. In many cases, old thermostats, you would even have to jumper Y1 and W1 together. We're going to pause here because I see you falling asleep. Older thermostats, Y1 and W1, we would actually jumper together. Why would we do that on some older thermostats? Why do you think?
Is it a heat pump function?
Because if it's a heat pump, Y1 and W1 are the same, right? What does a heat pump do when you need to run first stage heat?
Calls Y.
It calls Y with no reversing valve. What does it do when it runs first stage cooling? It calls Y with a reversing valve, right? So in older thermostats, you didn't used to have an installer setup. We're used to this now as a standard thing. Every thermostat has an installer setup. You go in, you tell it what kind of equipment it is. But on older thermostats, all the way back to mercury bulb thermostats, which are actually the standard when I started in the trade not that long ago. In 2000, people had mercury bulb thermostats everywhere. Isn't that wild? Kind of throws me off. Doesn't seem like 2000 should be 21 years ago, but it was. Yeah, so in those types of thermostats, you didn't have internal logic. So the only way you could tell it what kind of system it was by putting jumpers in place. And you'll still see some of these. You'll actually have physical jumpers in place. And so you had to jumper Y1 to W1. Nowadays, you tell the thermostat that it's a heat pump, and it automatically does that. It automatically just energizes Y in both heat and cool. Testing heat strip current. So 5 kilowatts, it's about 20 amps. But we talked about why it changes. If you're hooked up like we are here, because this is a 208 facility, quick question, why is this a 208 facility? What does it mean for something to be 208?
It's commercial setting, right?
Say it again?
Commercial?
It's going to be generally commercial. But why are commercial buildings often 208? Why is that? Because if I measure at the outlets here, what voltage am I going to get out of these outlets? You're going to get 120, right? But it's 3-phase, right? And so,
These are
hmm?
You're going to get 120 on these?
Yeah.
I guess I haven't really.
No, you get 120 still.
Probably that's what I'm for.
Because from leg to neutral, it's the same. It's from leg to leg. The two legs are no longer 180 degrees out of phase like they once were. So 180 degrees out of phase means that they're, like this. It would be, what would it be if it's thirds? It would be 90. Why am I all of a sudden having
It would
a
be like this. It'd be 120 out.
120 degrees out of phase?
Here
Yeah.
to
Wow,
here.
that was really weird. Whew.
It'd be from here to here.
Yeah. So because they're not, the phases aren't lined up, now you have a lower voltage between phases. So that's why you have 208. The point being that you're going to see 208 when the building is a 3-phase building and you're only using 2 legs, And that's what this is. This is single phase equipment hooked up to 2 legs of 3 phase. So when that happens, you're going to see lower output, which means you're going to see lower current. So just because you were to measure, 18 amps on this, you wouldn't, because you might think, oh, well, this heat strip's not working properly. No, it's just that the input voltage is lower. So input voltage lower equals lower output, lower current. 10 kilowatts is around 40 amps, but it's still 20 amps per strip. So if you imagine this is 10 kW, this is actually a 9 kW strip, but if it was a 10 kW strip, you'd have 5 and 5. So you could still measure them individually. You put your amp clamp on the black wire that feeds the strips, one side of the strips,
20.
Put your clamp on it, it'd be 20 each. If you went to the main leg that feeds it, your main input, or you put it under both wires at once, then you would measure 40. Make sense? Cool. But it's still going to generally be maximum of 5 kilowatts per strip. And this is just showing this. So if you look here,
You can take an amp draw on both wires at once.
yep. As long as you're not opposite phases. If they're on the same phase, then you'll measure the same. And these would be. If you took both blacks and put a clamp over both, you'd measure the cumulative amount. So this guy right here, what is this? 5 kilowatt or 10 kilowatt?
It's 10.
That was a trick question because this is the same one we just looked at. It's actually 9, but it's 2 separate strips. So
It's a 10.
yeah.
It says it right there.
This one right here, is this a 10 kilowatt or a 5?
It's a 10 too.
It's a 10. You see 2 separate strips, right? This guy right here, you can tell it's a 5 because there's only one. It's in the center. That's a 5. Now, it isn't necessarily, when I'm saying this, that could be a 3.5. But it's a single strip. All right, heat strip thermal limits. I'm going to pass this bad boy around so you can take a look at the thermal limits. This one's interesting because it's got thermal limits, thermodiscs on the high voltage side on each strip, and then it also has a low voltage thermodisc too, which also protects it. So it's got double the protection. Huh? Pass it around. It's fun. We're having a good time here. Everybody's enjoying themselves, So if you look at, oh, that's right. He was in the last class, wasn't he? He was in your
Last class.
hashtag
The
class.
last one.
Yeah, hashtag class. Yeah, that other class that happened. A couple different types here. We've got a fusible link, which I wanted to mention quickly because you will see these sometimes. This is a single fail
So is the one with the orange wires.
thermal overload. This one here is?
Yeah, that's what Eric told me.
What? Why?
He says he's pretty sure it's a single fail.
I don't think so.
There's a button right in the middle of it, you can click it.
No, just
Reset it, but if there's not, then it's a single fail.
auto reset. I still think it's auto reset, but whatever. The other thing you're going to notice here is they actually have temperature ratings right on them. So 150 degrees, and then it resets at 55 degrees less than that is what I think that means. Not that that really matters that much. This little guy here is 180 degree trip. So you can, if you pay attention, you'll notice a lot of interesting information. But if you see one of these, and one of these is open, you have to replace it. Now, how would you know if one of these is open? Or any of these? How would you know if they're open? Ohm it out would be the easiest way, right? So you take the wires off, take your ohm meter, obviously shut the power off first, measure across it. What are you going to measure if it's open? OL, infinite ohms. No path, right? If it's closed,
When it's closed.
maybe if your meter has that setting on it. But a lot of times I see techs don't have their meter on there, like it's not ringing out. I mean, you look down at the meter and it's reading 0, right? Or 0.1 or something like that. Well, look, it's reading 0.1. Is that good or bad? Low ohms means good path. Infinite ohms means bad path. Infinite ohms means open. Low ohms means closed, right? All these are switches. So they don't consume energy. They just open and close in order to protect the circuit. All right, what can we use to control a heat strip? The 2 top ones here, we show a heat sequencer and we show a contactor. So when we talk about control, I'm talking about the actual line voltage control. What actually turns the heat strips on and off? There are certain types of...
I'm telling you, it's the thermostat or something's wrong.
So you have relays, or they actually wouldn't call them relays, they would call it a contactor. that are rated for the current that a heat strip uses. Come on in, have a seat. Come on in, come on in, come on in. It's okay, it's good, we're having a good time. You have contactors. Some brands will use a big old contactor in there to turn it on and off, and some will use what's called a sequencer or a sequencing relay. The only thing to know about a sequencer that makes it different is that a sequencer, the contacts close at different times because it actually uses a heater. So rather than an electromagnet down here, it has a heater, and that heat causes these little round thermodiscs to snap at different times in order to make or break the circuits. So basically, when you see a sequencer, it's generally there because you're running things at a different sequence. You talk to him, Bert?
Yeah, but that might be just a few seconds, right?
Right.
Yeah.
Could be just a few seconds.
So it doesn't all come on at once.
Could be, or it could be so that you have a fan off or on delay too. So you get the point. So a sequencer brings things on at potentially different times, and they're generally designed to handle the current that a heat strip is going to have. I mean, again, it depends on what type of sequencer it is. But what you don't want to use to control heat strips, line duty, is a regular relay, like a 9340 or 9380. So quick pause.
I gotta go.
Yeah. Quick pause. Just going to address this again. Why do you not use a 9340 or 9380 to directly control the line voltage of a heat strip? Why?
Can't handle the amperage.
Can't handle it. You know, it can't handle the heat, so it needs to get out of the kitchen. Am I right? It's like Tom Cruise from A Few Good Men. It cannot handle the truth. You know what I'm saying? All right? 15 amps. That's all it can handle. 15 amps. So if it were a 3 kilowatt heater, it could maybe barely handle it, but that's not what we're gonna use for that. So this is for fans, blowers, condenser fans, that sort of thing, and then controls, isolation, whatever. It's not for heat strips. But what's interesting is we actually use it in conjunction with heat strips for a fan interlock sometimes, and this is where it gets a little tricky. And they may not always use a 9340, but they're going to use some sort of similar control. We're going to talk about that in a second. All right, let's talk about heat strip staging. Why would we stage heat strips if you had more than one? So that way they don't come on at the same time. You're especially going to see this in other markets where they have 15 and 20 kilowatt heat.
Less inrush current?
Yeah, it's brilliant, brilliant. Where'd you get that from? What else? What else? There's one other thing.
The less electric heat, the better.
The better, yeah. That's a good, you make a good point. The less electric heat, the better. So if you only need 5 kilowatts in order to keep up, then only run 5 kilowatts and let the heat pump do the rest, right? Because the heat pump is far more efficient than the electric heat. The other reason is if you bring on 20 kilowatts of electric heat all at once, how much current is that? It's not hard math. 20, 20, 20, 20. 80. Right, people count on their fingers, pull off your shoes, use your toes. 80 amps.
20.
80 amps all at once.
I thought you said if you bring on 20 amps all at once, how many amps is that? I was struggling with that.
Yeah, and again, I mean, whether you run 80 amps all at once or you run it slowly, it's not like it's that big of a difference. But if you don't need 80 amps, it comes down to the staging. If you don't need it, then don't run it, basically, if it were a 20 kilowatt. Any questions about that? I said we're only going to go an hour. We're already over an hour, so I'm going to finish up this class, and we're just going to leave. All right, how's that sound? Sounds fun to me. I like going home.
Where did you get that diagram? That is so nice.
Yeah, it sure is. It's right in my site, if you Google 9340
Wow.
or any of this stuff, you know. I have a website. It's got some good resources on it. It's a great place to prepare if you're going to give a class.
That would have been great.
Ayo. Huh? What?
That would have been great last class.
Yeah. Okay. So this just illustrates. Oh boy, somebody's gonna get it.
Wow. Ballsy.
You'll notice that these two actually kind of look the same. So this shows the coil. So that's these points here. So that's actually the electromagnet that switches its position. This is the normal position, normally closed between 1 and 2, normally open between 1 and 3. And you'll see they have this same diagram drawn on here. That's this guy right here. 1 and 2 are closed, 1 and 3 are open, right? If you energize it, what happens? From here to here it goes open, from here to here it goes closed. So, and this guy, same thing, same time. Make sense?
Yep.
All right, cool. So here's how the interlock is wired. We're just going to talk through this circuit very quickly. and then I'll show you how to think about this circuit if you ever have to wire it, because it's an opportunity for a big mistake. If we wire up this interlock in such a way that the heat strip current is being carried through the relay, we're going to melt the relay and make a big fire, right? Big stinky plasticky mess. So we don't want to do that. We have to make sure that it's set up in such a way. Again, back up. What's the purpose of the interlock again? Anybody remember?
Make sure the fan comes on.
Blower comes on with the heat strips. Heat strips are on, blower's on at the same time. That's the reason that it's there. Now, again, they're not always going to look like this relay, but the interlock's almost always going to be wired, if it's line voltage, it's almost always going to be wired in this same general way. We don't want, every time the blower is on, for the heat strips to come on, right? That would be bad. There's a lot of ways you could wire it so that every time the blower comes on, the heat strips come on. That would be easy to do, to make them both come on at the same time, but we don't want that. That would cause very high power bills, right? We don't want that. We also don't want the heat strip current to be carried through any of these contacts. Kind of tricky. So here's how this works. And this shows the terminal numbers on it. So if the heat strips go on, so this contact for the heat strip closes, both of these close, right? Imagine these close. You have voltage coming through here. This relay is already, regardless of whether the blower was previously calling, is closed, which brings on the fan, right? Current for the heat strips isn't being taken through any of these. Let's say that this relay is already on, so the blower was already on. Well, does that hurt anything? No, because the blower is already on. These close. It doesn't make it through to the blower, but the blower is already on, so who cares, right? Either way, if these heat strips are on, the blower is also going to be on. So rather than your blower relay backfeeding your heat strip relay is backfeeding your blower through a relay. That prevents the opposite from occurring, right? We don't want every time your blower is on for your heat strips to be fed. So let's look at it the other way. Let's say that we have we have a G call. So when it calls on, this closes and this opens for our blower to run, right? So now our blower is running. Can it backfeed our heat strips? Nope, because this is now open because you have a G call, right? So you get this. This is when you don't have a G call. This is what it's like. And when you switch it, it goes the other direction. 1, 3, 2. 1, 3, 2. Kind of complicated, but we're going to skip that. Here we go. So this is how you do it. Because this is where when people are given one, they do it wrong even if I give you the exact diagram to do it, because it just is counterintuitive. So you follow the ladder diagram closely to wire in a fan interlock. This is the very same thing that we just showed. Don't think about the relay right side up, flip it upside down. So now you're connecting power in, because when we think of power in, we always want to go to terminal 1 with power in, right? But is this show going to terminal 1 with power in? Nope. Power in goes to terminal 3. Power in goes to terminal 3, blower speed tap goes to 1, and then the load side of the heat sequencer relay. This is the most confusing part, because it's not the power in to your heat strip relay or heat strip control, it's the power out of your heat strip control, between your heat strip control and the actual strip itself, right?
So 2 will only ever be energized if the heat strips are calling.
2 will only, let's say that again. So 2 will only ever be energized if the heat strips are already calling, correct? Correct. Yeah, terminal 2 cannot be energized otherwise.
Yeah.
Because if the blower's not running, well, then there's not going to be any potential there.
Right.
If the blower is running, then that relay is going to be the opposite position, and this guy here is going to go open, which prevents it from backfeeding. Make sense? That's a standard heat interlock. Now there are other control strategies that just rely on the 24-volt call and it just uses a board, it doesn't use this sort of high voltage strategy, but this is the most common, typical long-term way that this is done. And this just shows, how you would actually wire that up in real life with a sequencer.
A lot of trains go through the same 9340 relay with low voltage. So you have the high voltage on the top, low voltage on the middle. High voltage for the blower,
yes.
Low voltage so they break common to the contactor going to the heat strips.
Yes, that is
From
correct.
4 to 6.
It also has that time delay relay on there as well to run the blower. That's that old school way of doing it in 9340. These are some standard things that you need to know how to do. You need to measure heat strip amps to make sure heat strips are running. That's how we can tell if they're running, right? You're not going to look at them. So you just clamp onto the black wire that feeds each individual strip, clamp, you're going to measure the current, right? You're also going to test it on and off. So it's not just a matter of saying, yep, I've got 20 amps, it's good, leave. Yep, I've got 20 amps, it's good, now shut it off. Make sure that, I know, and I don't mean shut it off with a breaker, I mean shut off whatever jumper you put in or whatever installer setting you put into the thermostat, and make sure that that 20 amps goes away. So test it on, test it off, force the system into defrost, and test the heat strip amps. That's a more complicated test. But if you ever have a system that's having an issue, especially in heat mode, if we get a cold snap, which happens sometimes, and you have a customer that's not keeping up or having challenges, that's something you want to check. Make sure that the defrost board is bringing the heat strips on when it's in defrost, like we talked about last class. All right, now this is our final little thing here, and I'm going to have our this is a good one for our senior techs here. So we're going to actually bring the whiteboard up here. Okay. So anybody who considers himself to be a senior tech, where'd Ronnie go?
He said he had to go.
I just had to go, huh?
Kid stuff.
Kid stuff, yeah, sure. I don't know what that's like. All right, so this is actually a code in a lot of places. I couldn't find it in the Florida code, but I thought it was here at one point. Like, nobody does it in Florida, but heat pumps having supplementary electric resistance heat shall have controls that, except during defrost, prevent supplemental heat operation when the heat pump compressor can meet the heating load. A heat strip outdoor temperature lockout shall be provided to prevent supplemental heat operation in response to the thermostat being changed to a warmer setting. The lockout shall be no lower than 35 degrees and no higher than 40 degrees. So typically it'd be 40 degrees. You set up a thermostat outside, a control, that unless it is below 40 degrees outside, your heat strips can't run. Now they're saying except in the case of defrost, but I'm going to ignore that part. How would you wire up a device like this? It's just simple. We're just going to imagine it's open and closed. So it closes when it closes when the temperature is below 40 degrees, and it opens when the temperature is above 40 degrees. How would you wire it in order to accomplish that mission?
Can I wire it any way I want to, or do you want the correct way to wire it?
I want you to wire it anyway. I want you to wire it the best way. What is the best way to do it?
To prevent heat strips from energizing unless the temperature drops below
40 degrees outside. Yes. This is actually a fairly good puzzle.
Got it.
Okay, show me.
Do I have to use that though? Can I just write something different?
What? No, you don't have to use this thing. Just again, this is just what an outdoor thermostat looks like generally.
Yeah, I don't know the three.
Who cares? You know, the open and close, whatever. It doesn't matter.
Okay.
So, in many cases, you're going to use a universal control that you just set the dial, and sometimes it's just going to be a snap action disc that's automatically set to 40 degrees. But the general idea is when it gets below 40 degrees, it's going to close and allow the heat strips to come on.
Okay.
Fishing lure.
Okay.
Okay.
All right. So there's our heat strips.
This is our
They just have a name. Okay.
Okay.
All right.
So the thermostat wants to turn on our heat strip, so it sends a W all the way to our condensing unit
Okay.
via one of our thermostat wires.
Okay.
Now this is a close on fall, aka the 40 degrees.
AKA.
And when it does that, it closes and then actually sends the voltage all the way back to our air handler, which energizes our heat strip relay.
How is that different than how we wire things now?
What do you mean?
How's that different than how we wire up units now?
Well, units now go directly from the thermostat to our heat strips, right?
So does that mean we have to run a separate wire from our thermostat all the way to our condenser?
No, you have spare wires for that. I think you have two extras.
You just run it out the W that goes into the defrost board, and you would still need to bring.
You just bring it back somehow. We'll take it back.
Hey, I was right. That's all there is to it.
You would need to bring it back.
Hmm?
You would still need to bring it back.
Yeah, and so this is not incorrect. It's just not really explaining it exactly how you would do it. So one way, the way that a lot of people would do it is they would use 2 separate wires, and they would actually run those out, and then they would make and break inside the air handler. But that's a waste of a wire. You do need.
Switch would, right?
What's that?
Is that just breaking it like a safety switch?
Like a safety switch would, right,
You know,
on the inside.
Putting it in, breaking it.
Yeah, but you have to use 2 wires in order to do that all the way to the outside. So in Sam's way, you know, I think what he's saying here on this very well drawn diagram is that rather than taking your white and connecting it to the white terminal or the white wire inside your air handler, you're just connecting your thermostat white and your condenser white together in the air handler. Then that's going out, and then you're running another wire, black, brown, green, whatever extra you want to use, and you're running that back from the condenser to the air handler, and then that one is what you're connecting to the air handler white. So the air handler white is only being connected from that wire coming from the outside. And so what that means is that unless that bad boy closes, it's not going to allow, and in fact, let's think here, you could actually do it, you could actually wire it in such a way that it would work the way that this code says. Because this is saying that if defrost runs, it will still turn the heat strips on. And so it would just, it's a matter of where you break it. So you would connect this rather than breaking it after in the wire coming back, you would break it in the wire going in. And then the defrost board could still send the white signal even if this was open. So in this case, even if this was open, if we did it on the wire in, the defrost board could still route it back to white. Yeah. It's kind of a hard diagram to draw because there's a lot to that, but.
You hook white from the defrost board to black.
Correct, and then you'd feed back, black back, yeah. Yeah.
What's the other way of doing it?
The other way of doing it, no, what do you mean? That is the way, this is your way. What I just said,
Yeah.
what I just said is your way, isn't it?
I don't know, I wasn't listening to the part. Listen to that my way.
So, here, we'll draw, look, I'm gonna actually try to draw it in a way that is visually, yeah, I know, I just,
Some systems have this built in with an outdoor.
correct. So, the typical, if you were gonna do this with an Ecobee, how would you do it?
The Ecobee does this already through weather app.
Correct. So the Ecobee, you just tell it what temperature you know to lock it out at, and it just does it with a weather app. Piece of cake. How would you do it with the Carrier Infinity?
Well, the Carrier Infinity weather app sometimes experience crashes.
Yeah, no, that's not what I'm talking about. The Carrier Infinity has an outdoor temperature sensor, right? So it doesn't need a weather app. It has an outdoor temperature sensor, right?
Not anymore.
Carrier Edge has the outdoor one, which is
Yeah.
No, it from the factory it has one.
Well, they still use the weather app.
They do?
Yeah.
Oh, okay. Well,
Not that they need to.
anyway, all right, I can't get this tape off. So, we're gonna go, air handler is gonna be in the center.
Can you take that tape off?
No. So air handler is going to have a W terminal here. Our thermostat's going to be here. We're only going to focus on our, well, we'll do a W2. We're only going to focus on this circuit.
Okay.
This is our T-stat. W2, and then our defrost board. So normally we would take this and connect it here and then here. But now what we're going to do is we're going to go into our air handler and we're going to wire knot together a wire that goes out to here. We're going to break with that outdoor thermostat control, we're going to break it here. And let's actually draw this properly.
Thank you.
So you're welcome. So it's a single pull, single throw, close on fall thermal switch. Booma! Sorry. Sorry, that was a little too much there. Whew. So then that feeds into our defrost board, right? And then from here, we would run a different wire back, and this would probably be our black or brown, probably black if we have that extra. So our defrost board could still send a signal to bring on the heat strips by itself, even if this was open. But in order for the thermostat to do it, this has to be closed in order to send it back. But another way you could do it, which would be the way that you would immediately think to do it, would be to take your, do you guys have something to share with the entire class?
Jacob called you dumb. He's making fun of you.
Did he really?
No.
I had to grab pizza, so I missed the.
would be to take two wires. Yeah, thanks. Would be to take 2 wires from the outside, and then when you bring, you would go in here,
Still be off the thermostat.
and you would go here, like that. But now you have to use 2 separate wires from inside to outside, so it's just a waste of an extra wire.
So if you were, let's say that you were at a 2-stage and you were using black for the second stage, then what color?
Then you could use, say, green. That would be a possibility.
Okay.
If you have a wire that's fuchsia plaid, you could use that one. You know, maybe if you had a chartreuse wire, use that. You know, light tan.
What color chartreuse? What is it the closest to?
I have no idea. All I know.
It's the ground wire that is going with your high voltage.
I have a question.
Breaker.
No, you cannot. I have a question for you. Encarnacion, what is her favorite color?
Light tan.
What is her favorite animal?
Puppies.
Puppies. What's her favorite hobby?
Volleyball?
And
Praising the Lord.
serving the Lord. Boom. All right, I think this class is done.
Okay, is this really mandatory? It says mandatory requirement.
This is from I don't know which code this is from. This isn't from the Unified Mechanical Code. But this is a code that is a lot of places. I'm pretty sure this was in the Florida code, or is. I just couldn't find it in a quick look. But it does exist everywhere, and it actually is a kind of a good idea. In terms of energy savings, it's actually a pretty good idea because you really don't need to run heat strips when it's warmer than 40 degrees outside. And heat strips really do run up power bills pretty quick. And it's actually kind of nice too because it's another thing that prevents your stupid thermostat from doing something stupid and running your heat strips stupidly.
Summer.
Stupid.
Or just loose wire.
Did I mention stupid?
Yeah.
I made Elise laugh. That was good. Isn't Elise just the best?
Wow.
Oh man, yay. Any questions? Anything else? No? Great, thank you. God bless America. Bald Eagle.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.